Page 181, problem 47. Hold a 100-gram toy car is at the bottom of a vertical circular portion of a track. It's given a speed of 8 meters per second. The radius is 60 centimeters. It wants to know what is the magnitude and direction of the force that the track exerts on the car. Okay. As usual, let's start by drawing a picture. So we're told that there's a track and then there's a big like loop-de-loop or something, right? Something like that. Pretty much the car is in a circle. And it is down here, it has a mass. Its mass is 100 grams, so 0.1 kilograms. Its velocity, the magnitude of the velocity is 8 meters per second. And the radius is 60 centimeters or 0.6 meters. Okay. Notice how I converted everything before I even start my calculations. It's just going to make things easier in the long run. Okay, so this thing is traveling through the circle, right? So it's going this direction. That means since it's moving it in this way, it's going to have a centripetal force pointing towards the center of the circle. Let's try here. Okay, it's also going to have a normal force. Let's call this is actually, let's let this be the normal force, because what I'm going to show you in a second, this will make sense. I don't know if you can hear that, but there's fireworks outside. Okay, this is the weight force. Okay, and so we also have a centripetal force. I mentioned that earlier. We'll call this a little bit less because the overall net force that's operating to keep this thing moving in a circle, to keep this thing here, we need a centripetal force pointing in this direction. That's going to be the net force. So the net force is the centripetal force. Let's write it here. Centripetal force is equal to normal force plus the weight force, right? So that means that mv squared over r is equal to the normal force minus mg. So we can actually figure out what the normal force is because we know all of this information. We know what all of these things are and what this is. So let's just plug that in and keep going. Okay, so we got 0.1 times 8 squared, what's it, kilograms times 8 squared, meters squared per second squared, over 0.6 meters, plus, what did we have here? What was it? 0.1 kilograms times 9.81 meters per second squared. That this is going to have units of newtons when this is all done, which is what we want because we're looking for a normal force. So this comes out to be approximately, let's see, this gives us a value of 11.64736 repeating newtons, right? And we can just kind of round that to be 11.65 newtons. Since it's asking for 3 sig figs, I'd say you could go 11.7 newtons. That's what I would say, since we're rounding. Okay, next problem. Number 59. We're given a banked turn, which is going to look something like this. So it's an incline. We have a car that's going around a track. Okay, let's straighten that out real quick. Okay, we're gonna have a weight force as usual, pulling straight down. We're gonna have a normal force pushing off of the ramp. Okay, and what else are we told? We're told, well, we're given the angle for the bank, right? We are given the radius is 150 meters. The angle is 22 degrees. And we're also given a static coefficient of friction that's 0.400. Asking us to find a range of speeds for which the car can safely negotiate the turn without slipping. Okay, so it's important to note here that we're actually going to have different cases. So as this car, recall that this is a car, right? So this is a car. I know it's a square, but that's because I don't want to draw a car. Okay, so this thing is going around a banked turn, right? So it's like making this loop on a track. And if it's going too slow, even like, let's say it's even like sitting, and it might start sliding. If this angle is great enough, this thing will just start sliding downwards, in which case the coefficient of static friction, or the static friction force, is actually going to be in this direction if it's going slow. If it's going fast, if it's going super fast, then it's going to actually start to go, it's going to climb up the incline, right? So it's going so fast that it can no longer be held onto the track. It's going to start going this way, which means that the coefficient, or what do we call it? We call it the static friction force is actually going to be in the opposite direction. So these are the things that we have to consider as we go through this problem. So let's look at the components. We can set this up before we really start to do anything. And since this incline is parallel with these forces, we can safely assume that this is going to go straight up in the air. This is over here. Sorry, that's not what we're assuming. We're actually going to assume theta is going to be up. Let's say this is coming downwards. This is going left. And theta is going to be here, right? If you don't believe me, you can draw some rectangle and say this is our incline. This is theta. This is a 90-degree angle, which means that this has to be some angle, right? And then this is going to be theta as well. Okay? So this is the same situation, I just drew it a little bit separate. So here's theta, here's theta. Same deal. I'll just leave this over here. We can use that for reference. So recall also from our other problems where we're dealing with blocks on inclines, that this is going to be theta. Okay, so that means that we have up here, we're going to go with the normal force components. By the way, our axes is actually going to be set up more straightforward than we normally do. And I'm only modeling this off of the book. So if you look in the book, there are a couple of examples of banked turns with cars and friction, and I'm going with what they do. So now we have y hat direction and x hat direction here. Okay. So we also have then, we have our x component of the normal force is pushing this direction. We have the y component of the normal force is pushing this direction. So this is F in y, this is F in x. Okay. Also, this is going to be F mu x, F mu y, F mu x. Remember that these are different cases. So I'm just drawing this at the same time to give you a picture, right? This is only going to be the case if this thing is going so slow that it starts slipping down. Here. So just to be clear, if this thing is moving slowly and starts slipping down this way, we have some weight force pulling it down, then this is going to be active. And oppositely, if this is going so fast that it starts going up the bank, then this is going to be active, okay? So we want to find what range we can have before those things start to occur. All right. Now if we consider that we have this, since this is I'm going to move this axis over here. Since this is a car going in a circle, and our axis is straight up and down, this is our y-axis, this is our x-axis, then we're going to have a centripetal force that pushes this thing straight into the center of the circle going this way. And we can have that, this normal force here is going to be the active centripetal force. Let's consider the frictionless case first, okay? So let's pretend that these friction vectors aren't here. And so what we're going to do is we're going to say, let's find, for frictionless case, just to set up, just so we have an idea of what's going on. It's not, we have this way and this way coming down, right? So it's not actually jumping up or down off of the bank. So it's going to be 0 in the y direction is equal to Fn y. Well, we could call this Fn y component here. Oops. Let's put our theta. Our theta is actually going to be here. Okay, so now we have Fn cosine theta minus mg is equal to 0, which means that Fn cos theta is equal to mg. That's what we get from our y component. And then for the x component, we're going to have, remember, there's no friction coefficient. There's no friction here right now. I'm only doing the frictionless case just for now. And so the x component is going to be the centripetal force. Okay? So that means we have mv squared over r equals Fn sine theta. Right? So that's Fn, oops, we're missing some information here. This is Fn y, so Fn x, so this is sine theta, right? So we're talking about the x direction, this is Fn sine theta, given that this is our normal force pushing off of the ramp, right? Okay, so now what we can do is let's add in friction and see what we get. So I only did this as a quick example. This is how we would normally do it, given our axes. Okay, it's a good idea to pause if any of this doesn't make sense to you yet, because I want you to be clear on this before you move on. So next, we're going to add in the friction. So we're going to say fast case. So now we're going to consider that this car is moving around so quickly that it's going to slide up the bank. Okay. So we're considering that this stuff is gone. All right? So we add in this frictional force, which means for our y component, we're going to have, I should have been more clear here, we're going to have mg, we're going to have Fny, and we're going to have the F mu y. Okay? So I'll show you what I mean. So let's go here. Now we have this minus the weight force. We'll just call this mg right away. Minus mg minus F mu y. And again, this thing is not jumping off of the bank or breaking through it, so it's all equal to 0. So we're in equilibrium in the y direction. In this direction, we're in equilibrium. Okay? Clarify that what I mean is I don't want this thing to actually slip. So we're looking for the minimum and maximum values that we can have before it starts to slip. So right now we're saying that it's not quite going down. Sorry, it's not quite going up the bank yet. We're just approaching the threshold. So right now there is no motion in the y direction. We only have a net force in the x direction, which is the centripetal force. Okay, so here we go. So now let's do x real quick before we break everything down. We have our normal force in the x direction. We're going to have our centripetal force. Oops. Sorry. Our frictional force in the x direction. I actually need to point something out before I move on, because in the book, what they do is they have their incline is actually opposite of what mine is, and they keep their centripetal force going this way as positive. So to be consistent with what the book does, instead of flipping this whole diagram around, I'm going to define the x direction as positive, pointing this way. Because our net force is going to be centripetal force, and we want it to be in the positive direction. Okay, so what that means is we have, since I'm talking about the case where the frictional force is pushing this way, this is also positive. So this is positive and this is positive. So here we go. X, and this is all equal to centripetal force. Okay, so let's break these down. Let's break them open, I guess we could say. So Fn, recall that this is that the theta was actually at the top, so this is cosine theta minus mg minus, I'm going to take this to the other side in just a second. Okay, and then the x direction, we have Fn sine theta plus f mu s cosine theta is equal to, what was it? Centripetal force mv squared over r. Okay, just breaking these all out. Same, not really changing anything. I'm just, we're using this vector here, and we're using this vector here, as well as mg, right? So I'm just adding up all of my force components. This one, and this one, for this case. Because recall, we're trying to find a range, so we're going to do the same thing for the opposite direction in just a moment. Okay, so let's make a note. Well, we can say that we need to recall that the frictional force is equal to the frictional coefficient, in this case it's static, times the normal force, right? So that'll help us simplify things a little further. So let's go to our x component first. So the resultant of the x component, what did we have? We have Fn sine theta. So we can just replace this coefficient here with us times Fn cosine theta is equal to mv squared over r. So that actually simplifies things quite a bit, and we can solve now. Let's say, since we're not going to really be able to figure out exactly what the normal force magnitude is from this, well, we actually probably could, but we want to solve analytically, because what we're doing is trying to find the range. In here in a second. So let's just solve for this. So now we have Fn is equal to mv squared over r times 1 over sine theta plus mu s cosine theta, which actually looks a little familiar because we just did a problem like this in the last lecture. Okay, so now let's go to the y direction. So what do we have? Oh, we're in equilibrium here, and we have, let's see, what was it? Here it is. Fn cosine theta minus mg minus the frictional force. Okay. Cos theta minus mg minus mu s frictional force. What was it? Sine theta? Yes. Sine theta. Okay. This is the reason that we were not able to solve analytically for the normal forces, because we don't actually know what is. We were not able to solve for the numerical value of the normal force because we don't know what the velocity is, and that's what we want. We want a range of velocities. So now, since we're on the y direction here, we have a way we can solve this. So mg over, what do we have? Cosine theta minus mu s sine theta, that's going to equal the normal force, right? So now we have a normal force, oops. We have a normal force up here from the x direction and a normal force from the y direction. Let's set these equal, because this is what we solved for was the magnitude. So we have two magnitudes. We can set these equal to each other and solve for this velocity. So let's do that. Okay, we have sine theta plus mu s cosine theta. This is going to be equal to mg cosine theta minus mu s sine theta. Now, just before I solve for this, which should only take a second, let's just recall what I'm even doing here. We're trying to find the range of velocities before this thing will start sliding up or down. So how fast or slow can this thing go before we actually enact these frictional forces, right? And right now we're considering the normal force and the weight force, of course. And we're going to the upper limit. So what I'm saying is how fast can we go before this frictional force going this direction starts to be enacted. So because if it goes too fast, it's going to slide up the ramp, and then we have friction pushing this way. Okay, that's what we're looking at right now. So what is our maximum value? So let's call this V max, right? And then we have M, well, let's take M goes away because we have this on both sides. We're going to have G times R times sine theta plus mu s cosine theta all over cosine theta minus mu s sine theta. This is all under a square root. So that's V max. This is we can go before this thing starts slipping off the ramp. Now let's find how slow can we go before this starts slipping off the ramp. We don't really need to go through this entire process again, because if you notice, what we're really going to do is we're just flipping the sign of the frictional coefficient. So in this way it was going down, right? So we had a positive x direction and a negative y direction. In this case it's going up the ramp, so we're going to have a positive y direction and a negative x direction, remember, because I redefined the x-axis this way to keep this positive. So what I'm saying is that just in every case we're flipping this sign for the friction, right? So these are all going to switch. So it switches there, it switches here and here, it switches here, and it switches, oh yeah, that was x direction, and then it's going to flip also here. So this changes and this changes, which means in effect, in both of our normal forces, the coefficient sign changes here and it changes here, which means that V minimum, so I'm just trying to save you a little bit of time, V minimum is going to be, this sign is just simply flipped around. And if you don't believe me and you want to prove it to yourself, by all means, please do, because it's actually kind of a fun problem to go through. And for the next part of the problem, we're asked to find, I mean, we want the range of the speeds, right? So remember that we actually have values here. I always try to plug them in at the very end. Oh, what did I do? Look at that. There we go. Okay. So we plug these values in to these equations. We come up with a V max that equals 37 point, let's just write it all down, 565 meters per second, which I'm going to approximate to about 38 meters per second. That's the maximum speed, and the minimum speed comes out to be about 2.2583 meters per second, which comes out to be about 2.3 meters per second. Which actually, that's a pretty large range. I wouldn't know what to expect in this situation, but it seems like quite a bit. So you can go anywhere between 2 something meters per second all the way up to 38 meters per second. That's a pretty big jump before you start to slide. Okay. That actually makes sense though, because you're saying that there's a low speed that you can start to move at before you slide down the ramp. but you really need to be going pretty fast to slide up the ramp and work against gravity. So that actually makes sense. All right. Next part of the problem, they want to know what is the minimum value of the frictional coefficient where the car's minimum safe speed is 0. So what they're saying is set Vmin to 0 and solve for your frictional coefficient. What is the frictional coefficient in the case that this is 0? Okay, that's what it's really saying. So, well, I'll just copy all this here. All right, we're going to solve for this. So we square. So, well, first let's set this to 0, right? Let's do it this way. Excuse me. Let's do it this way. Okay, so we square both sides. This square root goes away. Then we divide both sides by g over r, or g times r, excuse me, and that goes away, right? That's going to still be 0. Then we take this coefficient down here. So we multiply both sides by this coefficient. That's still going to be 0. So I'm just trying to go quickly so you can see what's going on. And then we're going to be left with this. Okay, so at this point you can solve. So we say sine theta equals mu s cosine theta. So now tangent theta is equal to mu s. Keeping the angle constant, then mu s is actually going to equal 0.404. And that's unitless, by the way. This is for a 22-degree bank. So that's the answer. Next problem, suppose numbers 24 and 25 on page 208. So now we're in chapter 7. Okay, so let's write that down so we don't forget where we are. Suppose a planet with mass m is orbiting a star with mass big M, and the mean distance between the planet and the star is a. Using Newton's law of universal gravity, derive an algebraic expression for the speed of the planet when it is at a mean distance from the star. So, okay, all that sounds pretty crazy, but this is really not too bad. The universal law of gravitation is this constant, universal gravitation constant, times we differentiate between our masses by making one big and one little, and then the distance between them is r. Okay. So let's notice that we have a star here. It looks like an egg. There's a star. And now we have some elliptical orbit, right? And a planet is making an orbit here. Okay, we'll call this is big M. Let's do this, call this little m. Okay, anyway, the point is that this thing is traversing an arc. In most cases, it's more similar to a circle. And it's going to have some centripetal acceleration towards the center, right? So what we have is let's take our planet out, and then g times m, which this thing is what's causing our gravitation, right? Because this is the more massive thing. G times big M over r squared. Now this is going to equal, this is little m times acceleration. This is exactly how we get acceleration for Earth. We take gravitational constant times the radius of the Earth times the mass of the Earth, and that gives us 9.81 meters per second squared. Okay, so we do the same thing for the star. We just say, well, this is ma. So now we have ma is equal to net force of some centripetal force here. So we have mv squared over r. So before I move on, I actually want to point out that this A is not the same as the A we're about to replace R with. So R is actually equal. We'll call it A prime. Because when we're talking about Newton's laws and we're dealing with acceleration, we need some way of differentiating what's going on, right? This is acceleration. This is A prime. The distance. This is a distance. Well, we didn't really. Okay, so here's what we're going to do. We're going to take m times gm, our acceleration, times little m times v squared over r. Okay, so let's just ignore this for now. So this is what we're left with. This little m is going to cancel, right? This r down here is going to cancel. So now we're left with v squared is equal to gm over r. That gives us gm over a prime, which was our distance here, okay? That's it. That's the answer. So this is its speed when it's at the mean distance from the star. As part of the problem, you're given some values, and you pretty much just have to plug them in. Let's see. The planet we're given is 2.44 times 10 to the 25 kilograms. The star, let's say, just call this planet. The star was 3.65 10 to the 31 kilograms. And the mean distance was 1.12 times 10 to the 12 meters. If this notation is confusing, all I'm doing is I'm writing down, this is how you would write it in your calculator or in some calculators. And so I just end up writing it this way, times 10 to the 31 kilograms. This is our planet. This is the star. And this is the mean distance, 1.12 times 10 to the 12 meters distance. Okay, so I just plug this stuff in. Remember that the planet was the thing with the centripetal acceleration, right? And so this m for the planet actually canceled out in the equation. So all we're left with is the mass of the star. So that's important. So anyway, I plug in G is equal to 6.67408. You can just look this up on Google. That's what I just did. It's also probably in your book, but I just am trying to make this super fast. So these are the units that you're given. I mean, this is, you would say that this is over kilograms over, what was it, seconds squared, right? So you can check your units at the end as well. So the reason I'm writing this out is so you can plug all this in. And remember that the planet mass actually goes away in the equation, so we're just left with these three values. And we plug these right into here. That gives us a value of 4.6633 times 10 to the 4 meters per second. Or 4. Let's say 7 times 10 to the 4 meters per second. Okay, next problem. For the next problem, number 28, we're given a setup with 3 spheres arranged in a 2-dimensional plane in the xy plane by figure 7.28. And then you're given values for these and you're given locations. It wants to know, assuming an isolated system, it wants to know what is the net gravitational force on the sphere located at the origin. Okay, I'm just going to draw this real quick. I'll pause and draw this because you don't need to watch that. Okay, so here's the diagram. Since we want to know what is the net gravitational force on the sphere at the origin, so we want to know what is the net gravitational force on this little guy here. So that means we need to calculate the gravitational force between these two, and we need to calculate it between these two. And since, let's see, M1 is the most massive sphere that in between both of them, because this one up here, M3 is, let's see, it's 8 kilograms. That's supposed to be an arrow. 8 kilograms. This one was 12.5 kilograms, and this one was 4.5 kilograms, right? So that means that since this one is the most massive here, that means that the gravitational force will be pointing these directions. So in the negative y hat direction from M3 to M1, and the positive x hat direction from M2 to M1. Okay. All right, so let's start calculating some things. So force, we'll call this F12. So we're going from here to here. So this is going to equal G from our universal law times M1 times M2 over the distance between them, R12, which in this case is just 6. We could do this with unit vectors and dot products, but we really don't need to. I mean, this is at 0, 0, and this one's at 6, 0. So the distance between them is 6 in the x direction, but it's just, we'll just call it 6. So now we have G times 12.5 times 4.5 all over, oh, sorry, this is squared, all over 36. So that's what you get there. Next, we do from here to here, right? So we have G, M1 is 12.5. M3 was 8 kilograms. Oh, I'll write it out explicitly first. M1, M3 over the distance between them. Right? That's going to give us G times 12.5 times 8 all over. Again, we don't really need to do much with this because this is at 0, 0, this is at 0, 5, so the distance between them is 5, which gives us r squared is 25. Okay? And then we just add it up. So this is what we call superposition. It really just means just add what you have. So call this equals 1, and then this is n. The sum of the forces is going to give us F12, that's plus F13, since we're just looking for the force on the center sphere, right? So that's going to equal G times 12.5, because these factors are common to both of these, right? So we have 12.5 here, 12.5 here, and G here, and G here. So I'm just factoring those out. Times 4.5 over 36. And remember, we need to keep track of the direction that these forces are traveling, right? So since this is more massive than this one, the gravitational force is pulling this way in the positive x direction. So I should have written that down here. And this one, the other one, this is more massive than this one, so it's pulling down in the negative y hat direction. And so again, I should have written this here, negative y hat. Negative y hat. So that gives us, here, now we have 8 over 25. So this is x hat, and this is y hat. Okay, so to be clear, again, this is pulling because this is more massive. The gravitational force is going this way, positive x hat, and because this is more massive than this one, this is coming down negative y hat. So we did F12, x hat direction, positive x hat, F13, it's going negative y hat direction, right? So then when we add them both up, we get the positive x hat, negative y hat, okay? So that means, say, net force is equal to, what did we end up with? We had, so you plug all that in. Remember that I just pulled this value up as well. So you can just plug this into your calculator, the G, right here, just so you can see it. 6.67408 times 10 to the negative 11 meters cubed over kilograms over second squared. Okay. So I plug that in, I get 1.00095 times 10 to the negative 10 x hat minus 2.56 times 10 to the negative 10 y hat. That's how many, this is in newtons, by the way. This is how many newtons we have in each direction. And then we want the magnitude is going to be 2.75 times 10 to the negative 10 newtons. I found the magnitude. I'm not sure if we're asked that. Let me see. No, it doesn't actually ask you for the magnitude, but it's not bad to find it. So if it just asks for the net gravitational force, that's this here. Okay, hopefully this has been helpful. See you next time.